Okay, so we are going to start looking today at Module 7. Module 7 is going to focus on CAM design and its kinematic analysis. So if we look at our learning plan here for Module 7, you're going to notice that we're going to be focusing on Chapter 9 in your textbook, and which is titled CAM design. Now, we are going to be breaking this up into 2 lectures. We're going to be, talking for a little while today, and then we're going to be finishing up the next time we get together. So we will be, if you would, lecture/demoing for our 2 times. Just like we normally do, kind of our regular rhythm. You're going to notice that we do have a page here for session recordings. I will be recording this session as well as the next one that we have. But you will see out there previous years' recordings. So if you needed to kind of reference those, feel free to do that if and they're labeled appropriately. You're going to notice that we do have practice problems. Okay, so if we click on the practice problems, it looks like we have 3 of them here. We're going to be doing, I think, all 3 today. Actually, if I'm looking correctly, so I think we're going to be doing all 3 today, but that doesn't mean we don't have stuff the next time we're together. So we will have things. But as we look at assignment number 7, there are 4 problems. So not as many as what we're normally used to, but you're going to notice that they're worth 20 points each. So there are quite a few steps on each one. So maybe the problems are a little bit longer, but the first 2 are going to cover what we're going to be going over today, and then the next 2 are going to cover what we're going to be going over the next time we're together. And as we go through our demonstrations and such, I'll get you familiar with how we will be submitting those and what the formatting is going to be required. So let's take a peek to get started on our learning plan number 7, and I'm going to open up the PowerPoint presentation, which is our outline through Chapter 9 in our textbook. Okay, so here in Chapter 9, we're going to be looking at and identifying different types of CAMs and followers, okay, and really finding out what's the purpose of a CAM and a follower and where they can be applied. Understand the benefits of different types of follower motion schemes. We're going to find out I think it's 4 main categories of motion schemes and when and why we would use those. Also, really the hands-on portion or the application portion is going to be looking at and constructing displacement diagrams and then also CAM profiles, okay? Using information from a problem statement. So first of all, in our first section here, which is 9.1, this is an introduction. A CAM is going to accept an input motion, and it's going to impart a resultant motion on a follower. I like to say that the CAM is, when we look at an overall motion, the CAM is the input and the follower is the output. Okay, so if we look at Figure 9.1, which is an engine valve train, okay, on page 223, which is right at the beginning of our chapter, okay, you're going to notice here that up on the top here, this is the cam shaft. So we'll kind of come back to that. It is in contact with what's called a rocker arm. For those who kind of work on engines or know a little bit about that, these terms probably sound familiar, whether that's a car engine or a small engine. If they're a 4-cycle, they work in this very same way. Then you'll notice that we have the valve stem, which is attached to the valve. Okay, and then up on the top here, we have a spring or a valve spring. That valve spring makes sure that there is always tension between the valve stem and the rocker arm, which then pushes up, if you would, so that that rocker arm is always in contact with the perimeter of our camshaft. Okay, so the way that this operates is that the camshaft is going to rotate. And you're going to notice that there is this, what we call a lobe on that camshaft, okay? And as you can imagine, as this rotates around and this lobe comes around, it's going to push down that rocker arm, which is going to push down the valve stem, which is going to control that valve opening and closing down here, in that combustion chamber, okay? Now, as it goes past that lobe, it's going to go back up. And so then that valve is going to come back up. Now, to ensure that that rocker arm is always in contact with that camshaft as it rotates, that's the purpose of the spring here, okay? So when we look at a cam as it rotates is going to control the motion, in this case, of the valve. And the valve is going to move vertically or linearly. So we're taking rotational motion of that cam, and we're going to find out that we're going to time it so that our valve in this case vertically or linearly goes up and down at certain times. Okay. And then that rocker arm is what we're going to find out is called a follower that will then impart that motion on that valve. Okay. So many times what we're going for is when we go from the input, which would be the camshaft here, we're going to have an output motion then ultimately that is going to be linear in nature. Okay. And it's going to be timed based on the rotation speed of that shaft. Okay. So kind of a nice application and usually something that many people can relate to, but hopefully even if you haven't come upon this application, you can kind of see how things would work here in terms of that cam follower arrangement. Okay. Okay. Now, a cam can impart a very distinct motion to its follower. Okay. It's used to obtain, if you would, unusual or irregular motion that would otherwise be difficult or impossible to obtain with traditional linkages. So it takes really a very simplistic approach and a very, I don't know, very minimal number of parts to really go from rotation motion to linear motion. And it's really just through the shape of that cam that's going to get that follower to go up and down in this case. Okay. Now, cams are used in automation sequences, in this case, in engine sequences, and most of the time, they're going to have that timing element associated with them. Like when we want to move down, when we want to go back up, how long we're going to do that. And that's all dependent on the rotation of that shaft and the profile of that cam. Okay. It's very cost effective because there's minimal parts to do that with. And there's not like, if you would, programming involved. It's just rotating a shaft and that follower just has to remain in contact with it. Okay. Now, as you can imagine, there's a lot of different types of cams. Okay. And we're going to look at three main types. Okay. So if we look first at figure 9.2 up at the top here, these are a couple different types of custom cams. Okay. So each one of these you're going to notice has a bore. Okay. And that bore is going to be mounted to a shaft that's going to rotate around. Okay. Now, in some cases, there's a key to ensure that it is going to rotate at that same speed as the actual shaft itself, or it can be clamped down or mounted so that it's going to have that same rotational speed. Okay. But something you're going to notice is that this is not just a simple circular outside diameter. This is kind of an irregular shape around the outside, and that is what's going to control the motion of the follower that's going to be in contact with it as it rotates around. Okay, so this is the cam itself. Okay, and that's going to be mounted to a rotating shaft, usually coming off an engine or a motor or something like that. Okay, down at the bottom here. I should go in order. Oh, the next one. So we looked at custom cams, and then the next one is going to be the cam type. So there are a couple different types that we're going to come across. So at the bottom here in figure 9.3, the one in part A here of this illustration is going to be the most common that we're actually going to be focusing on. Okay. And this is just simply called a plate cam. So you can see that it's a flat plate that is then going to have the bore for the shaft that it's going to be mounted in. And then the profile of that cam is going to then be, custom to whatever the motion is that we need to have our follower follow. Okay. The next type is going to be a cylindrical cam. And what you can see here is that the cam actually fits down into a groove that is in this cylinder. And that cylinder is going to rotate while the follower, goes linearly back and forth. Okay, as it, kind of rides in that groove, if you would. And then the third type is going to be a linear cam. Now, in both cases, the cam itself is going horizontal. And as the follower, which has a pin that is going to follow in that cutout or that curve inside of that cam, is then going to cause that follower to go up and down. Okay, so like I said, the most popular and the one that we're going to be focusing on is going to be the plate cam. Okay. Now, just like different types of cams, there are different types of followers. Okay. Now, the follower is going to take a couple different forms, popular forms. Now, they can be variations on these, but these are the ones that we're going to see most often. The first one we have here is called a knife edge. Okay. And this is figure 9.4. Okay, at the bottom of page 224. The knife edge is simply just a point, okay? Not used a ton for a number of different reasons, and mostly because you're going to have large stress concentrations all on one point. But for low speeds that don't require really high forces, this ends up being a very simple way of obtaining the type of motion that you want. Now, as we look at this plate cam, okay, as it rotates around, you're going to notice that the center line of our knife edge follower, if we take that center line and extend it all the way down, it is in line with the center of rotation for that cam. Okay, so where that shaft is rotating, we're looking at, is that in line? So that would be an inline knife edge follower. Okay. The one over on the right here, this is a pivoting roller follower, and it happens to be offset from the center line. Okay, offset from the center line because the center lines, there's a distance between. Doesn't look like there's much of a distance, but it is offset. Okay, so as this goes around, you're going to notice that it has a roller that actually rolls along that perimeter. And instead of going vertically up and down, it's actually just going to pivot on a radius, okay, as we can see here. Okay, so that's another type of very popular follower, which is called a roller. The next one that we have down here in part C, this is an offset. Okay, so this has linear motion going vertically. And if we extend that, notice that it does not go through the center line of our shaft rotation on our cam. There is an actual offset intentional distance there. So that's called an offset. Now, the type of follower here is what is known as a flat face. So it's just friction, between the surface of the cam and the actual follower face there. Okay, but as it rotates around, it's going to move up and down here, okay, vertically. And then lastly, we have another pivoting. And in this case, we have a spherical face on the end of the follower, as opposed to, as we saw up here, a roller. So just another version of. Now, when we would use one or the other, usually depends on, what the output motion, first of all, needs to be. If you need something to pivot, then you're going to have a pivoting type of a follower, obviously. But if you need something to physically go up and down, then it's going to be more of that inline or an offset type of a follower. Additionally, the type of contact that you have with the cam is going to depend on the application. When we have things that are more high speed, a roller tends to be the one that we put in contact. If they're low speed, then things that are going to be more that friction type of application is going to be what we use. I guess for obvious reasons, if they're high speed where the cam is going at a very high speed, because of it being a friction surface here, you can imagine that heat is going to build up a lot more than if we would have a roller on an application like this. Now, the other thing I want to let you know is that even though we just see a roller over here with the pivoting follower, a roller can be put on an inline or an offset. Again, the roller, any one of these can be interchanged with any one of the types of followers that are there. Does that make sense? Like the faces, if you would. Okay, so a roller isn't only on a pivoting. A roller can be on an inline or an offset. Okay. And the same thing for any of the other faces on those followers. So again, we've got cam arrangements here, with the plate cam being the most popular, which is going to rotate about the center of a rotating input shaft, okay? And then the follower is going to produce the output motion that we need. So any cam arrangement, if we're designing a cam, we're also designing for the follower as well. One other criteria on the follower is that it always has to be in contact with the actual cam. Now, there are a couple different ways that we can do that, but the most popular is going to be usually a spring. Okay. Now in kinematics, we're going to be in the very early stages of the design process. Sizing a spring and incorporating into design would be further down the line in the design of the assembly. But know that as you're thinking about the early stages of design, like right here, even though we don't show a means of keeping it in contact with the cam, we do have to build that in. Okay. And like I said, a spring is a very popular one. If it's a low speed, you probably could use gravity. Okay. That would be okay. But if there's any type of significant speed, meaning rotational speed of that cam, you have to have some positive means of keeping it in contact. Otherwise, it's not doing what it's supposed to do. The cam isn't imparting motion if it's not in contact with that follower. Okay. And then you can have like jams and, just bad situations. So we want to make sure that we know that. Now, there are different types of follower motion, and we had already kind of looked at these. There's translating followers, okay, and those are going to be the ones where translationally that's going to be that linear motion. So in the case of A and C, which are in that figure 9-4, those are going to be the linear or translational motion. So the knife edge in this case and the flat face, okay? And then we can have the pivoting, okay? And the pivoting just means that we have a fixed center for our follower to pivot on, okay? And again, any one of these types of faces on our followers can be on any one of these arrangements, okay? So we already talked about follower position. It can be either inline or offset. Okay, so if we extend that center line of that motion of that follower, if it goes through the center line of the rotating cam, then that's an inline. If it's offset, then it's considered an offset, or there's a distance between there. We talked about the follower shape already. Okay. And then we're going to look at the prescribed follower motion. Now, as we had said earlier, think of your cam arrangement as the cam itself is the input, the follower is the output. So when we're designing, it's usually the output that we're more concerned with, especially in the early stages, because it's like, okay, what do we need to happen? All right. And then we design the cam to do that. All right. So the follower is really where we start. Okay. So when we look at a follower motion, the first thing we want to know is what is the total amount of time that we need to do what the follower needs to do. Okay. So we're going to add up all the individual times of the stages of the motion as it goes through one revolution on that cam. Okay. So for instance, we're going to take capital T here as meaning time. So the total amount of time, I don't know what I means. Maybe it's of the individual sequences. I'm not exactly sure. But we're going to take the time one, T1 is going to be, okay, what are we doing at the beginning of this cycle? Then the next one is going to be 2. What are we doing next and next and next? And you can have, an infinite number truly of sequences with however much time you need to do that. Most often it's going to be between 3 and 5 sequences for the motion that we're going to see in the problems that we're going to look at. Okay. Then once we know how much time it takes to go through the full motion of that follower needs to do, then what we're going to do is we're going to determine, all right, if we know the total amount of time to go through the motion, then what is the angular speed of the cam? Okay, because the total amount of time is one revolution on our cam. If we go back and we look underneath here, I'm going to go back to that original diagram here. So if I know that I want this, for instance, to go down 1 inch, okay, and then back up, however long I'm saying, if this needs to go down, let's say I'm going to go down, and I'm going to take 1 second to go down 1 inch. And then I'm going to dwell, or I want to wait just another second, okay? And then I'm going to go back up in one more second. That would mean that my motion is going to be 1, dwell for 2, and then my time 3 would be coming back up. Okay. Now, all of that, those 3 sequences are going to happen in one revolution of our cam. So if I took 1 second to go down, 1 second to dwell, and 1 second to go back up, do you see how the total time there is 3 seconds for one revolution? So I would have one revolution per 3 seconds. Does that make sense? And that's going to tell us what our angular, let me go back to my PowerPoint, what my W or my angular velocity would be. So you're going to notice here that this says one revolution. How long does it take to go one revolution in the total time for the sequence that I have up here? Okay. Now, once I know what that is, I then can figure out, okay, however many sequences I have, how many degrees in that one revolution does each one of those sequences take up? Okay, so we're going to be kind of working through this. So we're going to take the angular velocity and we're going to multiply it by the individual time from above. Okay. And then we're gonna multiply that by 360 degrees to find out how many degrees. So we'll kind of work through this, okay? But this is just kind of a snapshot of the different things that we're going to be aware of. Okay. Now, if you wanted to, you certainly may write down these equations on an equation sheet, but you're going to find them starting at the bottom of page 225. I have them on this PowerPoint to the top of page 226. Okay. I'm going to let you decide if you want to do an equation sheet or not. There's just these 3, and I think they're located in one place in the book that I think it's easy to find. So we're going to do example 9.1 together, and we're going to use the equations that we just kind of introduced or looked at. So if we go to page 226, you're going to notice that we have example 9.1. Okay, example 9.1. I'm going to zoom in here and focus. Says that we have a cam, which is right down here, is used for a platform that is going to lift boxes from a lower conveyor to an upper conveyor. Okay, so you can see here's a lower conveyor. All right. And then, oopsie, I'm sorry. Here's the lower conveyor and here's the upper conveyor. All right. So as this rotates around, okay, we want to go from the lower to the upper. So we're going to move this follower up and down, up and down. All right. Now, this machine is shown in the figure that we see here. We want to plot the displacement diagram and determine the required speed of the cam when the follower motion sequence is as follows. And they show it just below the figure 9.5. So we want to rise 2 inches in 1.2 seconds. So that means that we want this platform to go up 2 inches, and we want to do it in 1.2 seconds. Then we want it to dwell. What dwell means is we're just going to sit there. That's it. Okay. And we want to dwell and sit there for 0.3 seconds. Okay. And then we're going to fall 1 inch in 0.9 seconds and sit there again for 0.6 seconds. And then we're going to fall 1 inch in 0.9 seconds. And then we're going to start all over again. All right. So in one revolution, we want to do these 5 things. Okay, those 5 things. So I'm going to grab out a piece of paper. This is going to be our first practice problem that we're going to do for Module 7 practice problems. So at the top here, I'm going to do example 9.1. And this is on page 226. Okay, 226. Now, I'm not going to rewrite the rise, the dwell, because this is our given, if you would. I'm not going to rewrite those because they're right there. But we're going to kind of jump in, and we are going to first calculate the amount of time that is in one cycle. So a cycle is when our cam goes around one revolution. So how much time do we need to go around one revolution? And that's going to be the total time of our sequence that the follower needs to take. Okay. So the total time, and this is going to be the summation symbol, Ti is going to be equal to T1 plus T2, 3, 4, and T5. And the reason we have 5 T's is because we have 5 steps in our sequence, and that was identified right here. Okay. The rise, dwell, fall, fall. Okay. So we're simply going to take those times. And so T1 of the rise in 2 inches is 1.2 seconds, plus the dwell of 0.3 seconds, plus the fall of 1 inch in 0.9 seconds, then another dwell for 6 or 0.6 seconds, and then we have one last fall of 0.9 seconds. Okay. Now, something I'm going to let you in on is when we look at the sequence, however much you rise, make sure you fall. Okay. So you'll notice here we rise 2 inches. Make sure that when we fall 1 inch, that we fall another inch, somewhere along the way before we start back over. And indeed we do, okay? Because otherwise we're not going to have a nice transition. Okay, so if we add all of these up together, the total time should come out to be 3.9 seconds, right? 3.9 seconds. So that means one revolution of our cam is going to take 3.9 seconds. So step number 2 here is going to be to calculate the rotational speed. Okay, so that's going to be our W, our angular velocity or rotational speed is going to be how much time does it take to go one revolution. Okay, so one revolution of our cam, we're going to divide by the summation of Ti, right? Okay, so this is going to be one revolution divided by 3.9 seconds. So that's going to be equal to 0.256 revolutions per second. Okay, that's going to be equal to our W. So I'm going to put a little cloud around that because that's going to come in handy. Now, this is nice for, revolutions per second saying, okay, and we're going to find that that's going to come in handy a little bit later, that version. But if we were wanting to buy a motor and make sure that it was rotating at the proper speed, would this be very helpful to us? No. What do we want to convert it to? RPMs, right? Yep, because that's what we want to report in. So we're just going to go like this. We're going to say, okay, my 0.256 revolutions per second. I'm just going to do a quick conversion. 60 seconds goes on top, 1 minute on the bottom. And our W, if we were to report it and want to make sure that we size an appropriate motor or engine, we want to make sure that it is capable of going around 15.38 RPMs, right? That would really be what we would use. Does that make sense to everybody? Okay. We want the per second because that's going to come in handy in just a bit, but reporting it out, if you would, it's going to be the 15.38. Okay. All right. Any questions so far? So what is the revolution of the cam in order to complete the 3.9 seconds? Okay. Step number 3 here now is going to be determining the cam rotation for each one of the follower movements. Okay. So we know that the cam is going to go around 360 degrees in, or one revolution in 3.9 seconds. But if I want to know how many degrees of that one revolution, how many degrees of the 360 degrees does T1 take, or step number 1 take? And how many degrees does T2 take, and 3 and 4 and 5? That's what I want to figure out now. So what I'm going to do is those are called betas. Okay. So we're going to calculate beta 1, and beta is going to be how many degrees of that, of the rise of 2 inches in my full revolution does that take? So we're going to take the cam angular velocity, okay, and we're going to multiply it by T1, okay? Now, notice that T1 is in seconds, right? If I multiply it by the RPMs, I'd have to convert back, but I already have revolutions per second here, right? Okay, so we're going to take the 0.256 revolutions per second, okay? And we're going to multiply that by 1.2 seconds. Now, our seconds are going to cancel, right? But I'm in revolutions. I want beta in degrees. I want beta in degrees. So I'm going to do a conversion here. Write the conversion you think to get revolutions into degrees. What would I put, write in what you're going to put on the bottom and what you're going to put on the top. Okay. I've got revolutions on top here because technically this is over 1, right? Did you put 1 revolution on the bottom and 360 degrees on top so that the revolutions would cancel and now I'm left with degrees? Okay. So that means that beta 1 is going to be equal to that number. What do you get for a value? 256. I got 110.6 degrees. You guys get that same number? Okay, I'll pull the chat box out just in case anybody wants to chime in. Okay. Awesome. Thank you, Aiden. All right. So this is how many degrees of 360 that we're rising that 2 inches. Okay. Let's do the next section. So for T2, we're going to stay in the same spot for 0.3 seconds. So we're going to do that very same thing. And I should put my little cloud around here. Beta 2 is going to be W, angular velocity of that cam, times T2 this time. So this is going to be 0.256 revolutions per second. Okay. And then we're going to multiply that by the time 2 this time, and that's 0.3 seconds. 0.3 seconds. Seconds cancel. I'm in revolutions. And now I want to do my 1 revolution, 360 degrees on top. Revolutions cancel, right? I should close that up. So my beta 2 this time $27.6. Okay, and then we just need to do it 3 more times. So go ahead and do beta 3 and beta 4 and 5. Okay, so for the last three, you should get beta 3, 82.9, beta 4, 55.3, and beta 5, 82.9. Okay, I'll give you, looks like there's some people still finishing up, which is okay. These answers are also consistent with what they have at the top of page 227 in our book. Okay. So what we've done is for each one of the time sequences, the steps, if you would, in the motion for that follower, we've broken it into, we were first given how much time, okay? Then we found out for one cycle, how fast that shaft has to rotate. And then now, how many degrees does each one of those motion sequences take in a full revolution? Now, as a check, and I will require you to do this for yours, what we want to do is we want to find out, are all of our betas adding up to 360 degrees, right? We don't want to just blindly be like, okay, those are the numbers. And what we want to do is we want to make sure that 360 degrees is equal to the summation of the betas, right? So if we sum those up, beta 1 was 110.6 degrees. Beta 2 was 27.6 degrees, 82.9 degrees, plus 55.3 degrees, plus another 82.9 degrees, okay? And if we add those up, do we get 360 degrees? We do. I'm pretty confident, but it's good to check. I get 359.3. Yeah. 0.4. Okay. So very, very super close. Yeah. But we can call it, we're good because we know if we would hold it to that second decimal place, we would be even closer. So it's a good check. If you're off by degrees, then you want to go back and double check to be sure that you're good. But essentially, yes, we're right there. Okay. So it kind of like this is a check just to be sure that one revolution, all of our betas add up to that 360 degrees. Now, what do these numbers mean in terms of, because the problem wants to us to create what we call a displacement diagram. So for the practice problem, these are the calculations I want you to do, okay? We're not going to regenerate the displacement diagram that they are showing at the end of the problem on page 227, okay? We will get that chance in the homework that you do, okay? But I want to show you what a displacement diagram looks like and the different elements that we just calculated, how it's related here, okay? Now, a displacement diagram is a graphical representation of follower displacement, okay? Follower displacement. Remember, we started design with, if you would, the end in mind. The end is the output, which is the follower. What do we want it to do? We identified that we wanted it to rise 2 inches in 1.2 seconds, okay? So let's look. Our vertical axis, what is our highest number and where does it line up? 2 inches, right? This is follower displacement in inches. 2 inches is going to be on that vertical axis, okay? And then it says we want it to rise 2 inches. So notice in that sequence, we're up here at the top. And if we go down and we line this up, notice that T1 is just past 1 inch, which would be about 1.2, right? Okay. So this is the motion at the very top where we go up, we rise 2 inches. All right. That corresponds to the time, which also corresponds to the number of degrees along the x-axis. Notice that we start at 0 and we end at 360. This is one revolution of that cam. Okay. So of that, in that first T1, beta 1 is the number of degrees, which was 110.5, that it takes for that first part of our motion, the rise of 2 inches, right? Okay. Then you're going to notice as we move to the right, we've got a beta 2. Well, that corresponds to step number 2, which was a dwell of 0.3 seconds. So on our displacement diagram, we get up to our 2 inches, and notice we just show a straight line. We're going to stay at 2 inches for 0.3 seconds. So if we go down here, T2 is the difference between 0.2 or 1.2 and 1.5, which is 0.3 between. And you'll notice that beta 2, if we would take 138.1 minus 110.5, we should be getting 27.6 degrees here, right? Okay, so now what we've done is we've taken beta 1 plus beta 2, or time 1 plus time 2, or sequence 1 plus sequence 2. All right, now we're going to add to it 3. Okay, so our time 3 was, what was time 3? 0.9 seconds, and we fell 1 inch. Okay, so notice when we go from our 2 inches that was up at the very top, we only fell half that distance, or 1 inch, in a time of 0.9 seconds. Okay, so if we take our time here and we add 1.5 plus 0.9, we're going to get to 2.4 along that axis, right? Additionally, our beta 3 was another 82.9 degrees. So if we take 138.1 plus 82.9, we'll be at 221 degrees on our rotation. Does that make sense, everybody? Kind of following along? Then we do another dwell. That's this flat again. And that dwell is for 0.6 seconds. That corresponds to T4, which was 0.6. So if we take 2.4 plus 0.6, that's 3 seconds now along the time of our 1 revolution. And then our beta 4 was 55.3. So if we take 221 plus 55.3, we should be at now 276.3 degrees. Okay. Then the very last part here is to drop the last 1 inch, because if we went up 2 inches, we've got to come down a total of 2, back to our starting point, if you would. Okay. And now we want to do that in 0.9 seconds again. Okay. So you'll notice here we have 3 plus 0.9 is 3.9 in time. And then from what was 276.3, if we add 82.9, brings us to the very end here of our revolution. Okay. And notice that we're down at the bottom. So if you would, 360 is that same 0 over here. So we should start and end on that horizontal axis. Does that make sense, everybody? Okay. So a displacement diagram is a visual representation or a graphical representation of that follower motion. Okay. And in this first part of chapter 9, this is what we want to create. Now, when you create your displacement diagram for your problems, you're going to do 2 problems like this. All right. There's a little bit more that we have to go over. I'm not quite done yet, but you're going to do the calculations that you see here, okay, that we went through. We did the betas, and you are going to create a displacement diagram, but it's not going to be sketching it or doing it in Excel. We're going to do it in AutoCAD. All right. Now, proportions. I'm going to repeat this a couple times, but this will be the first time you hear it. As we look at the height here of 2 inches, you might wonder, well, how long should I make that x-axis? You're going to make the x-axis 3 times longer. Okay, so for instance, if I have 2 inches here, I'm going to make this 3 times longer. So the distance from the start or from left to right here is going to be 6 inches total. Okay. And then if I wanted to figure out how many degrees, like how long is a degree, because I have to break these out into degrees and time, right? Then I would simply take my 6 inches and I would divide that by 300 degrees, because that would give me how many inches per degree. You do not want to plot this out 1 inch, for instance, per degree, because this would be 360 inches long. That's not practical, right? Right? It's going to be way too long for how high it is. So proportions, whether you're in metric or in English, whatever your height is, your largest rise, your total rise, your highest point, you're going to multiply that by 3, and that's going to set the length. Does that make sense to everybody? Okay. So that way, like I said, proportionally, you'll have a nice look. And then as far as labels, this is just like a regular graph. It's a line graph, if you would. You're going to add what you see here. This is what we're going to duplicate. Okay. That's why we only have 2 problems for this placement of diagrams. Okay. Because there's kind of a lot here, to construct. Now you might be wondering, well, how do we get those curves in and out? That's going to be the next thing that we discuss. What I'm going to do is, this is a good point where we're going to take our first break, or our break today. So when we come back, we're going to continue on and look at follower motion schemes and how we're going to be constructing these ins and outs as we look at the diagram. So we'll take a 15-minute break, and then we'll be back to continue on. Let me stop our recording here.